because we are in a learning phase, that is very important that we all understand that what our course is about. I'll just open the PPT. I mean, just for our understanding. Right. Just one. Share. Right. Okay. Is my screen visible?
Yeah.
Okay. Yeah. Thanks. Okay. So actually, before starting with the class, because for next 12 weeks, I mean, including this one, we all will be understanding, learning from each other, and having a lot of interactions. uh, let's introduce ourselves and let's know what are your motivations to see this course, so that it will be very helpful for me, because see, all the lectures that professor has in this course is recorded. So he has taken his class, and that is actually, this course is actually a rerun. So there would be chances or instances when things will go out of your I mean, scope, or I mean scope of understanding, or there might be some difficulties that you want to ask, or there would be some interesting questions that you, because every individual is an individual, so you might have some questions that might not have come in their courses. So it would be much helpful for me if you could introduce yourselves and what is your motivation to join this course. And even if you want to say no, I mean, just once again said something. Yeah, yeah, Rohit, please.
Yeah, you asked for an introduction, so I just
Yeah.
wanted to. Yeah, I'm Pawan Kumar. I joined using I'm using my friend's laptop, so with
Okay.
his permission, I have joined. So I did my MTech in communication and signal processing. So I wanted to know better about estimation and detection theory. So to gain in-depth knowledge in this theory, basically estimation and this one. So
Hmm.
that's my motivation to join the course.
Okay. Pawan, are you
Pawan.
actually having some applications in your mind? I mean, you are right now a BTech, MTech, PhD student, or something like that, or you are an industrial person, something.
I work in an industry. Currently, I'm working as a software engineer in Cadence Design Systems.
Okay. Okay. Nice.
Uh,
Sambhav.
Hi, I'm Sambhav Kumar. I have done post graduation in economics.
Hmm.
So my motivation for the course is to learn basically the time series analysis for doing research and all.
Okay. Okay. Rohit. So I'm actually very happy that we have someone from economics, someone from signal processing in electronics. Rohit, you are from? Okay. Uh, Abhinav? Okay, okay, no problem, Rohit. No problem. We can listen to you. We will listen to you next time. Surely. Abhinav?
Hello, sir.
Yeah, Abhinav. Do you want to
Uh,
introduce
I'm
yourself? Yeah, yeah,
uh,
please.
I am a third year student, and my main goal is to uh, learn from this course. I want to mainly use this in real world application.
Just for fun, or is it like you are trying to answer the questions? Because see, this is very, very. I mean, I will be very happy that you are interested. But
Just I
if
have
you
free time.
okay, okay. So I would be actually very happy. I mean, I would suggest you take some thing in your mind. For you are doing a bachelor's in which stream?
Mathematics.
Okay, okay. So, oh, mathematics. I did not thought of that. But yeah, if you're doing in mathematics, irrespective of any field you are, you can take one real life problem, and because see, this Sambhav is there, Pavan is there. They are actually these engineers. They will apply somewhere. So if when we learn something new and when then we apply it to somewhere else, that sticks to our mind and actually poses some more questions. So if you're going to not thinking that forward, I would request if you could think, at least think of some question in your mind or some or the other thing that you can apply it. So if you personally, this is not nothing to show anyone, but you yourself will feel very happy. That's just an advice. Yeah,
Yes,
Arun.
sir.
uh, you would like to introduce yourself, Arun? Maybe his network is not working properly. Kartigai, Selvan?
Yeah, hello.
Yeah, Kartigai.
I'm from chemical engineering background.
Okay.
Currently, I'm working with the industry, so I want to know about data-driven modeling. So that's
Okay,
why
okay.
I'm taking this course.
Yeah, yeah. Nice. So actually, this is one of the few courses that actually anyone encounters anytime where you build models using data, because all of the even sir has specifically said in his core classes that a lot of courses that we see in chemical engineering or especially all engineerings are mostly first principles, but when you come to understand real time data, your first principles barely work. Sahara, would you like to share, I mean, would you like to introduce yourself?
Good evening. My name is Sahara Sarde. I'm from Pune and I'm currently pursuing BSc in statistics.
Mm-hmm.
And I got interest in time series because time series was introduced for us in our SEM 2. So from that, I have got interest in this subject
Oh,
and
you
want
have
to
already
learn.
read it. I mean, have you studied this time series?
Yeah, somewhat थोड़ा बहुत सीखा है.
Wow, nice. Very nice. Himanshu?
Yeah, hello, good evening, everyone. I'm Ivanshu Pandey. I'm currently in my third year BTech. I'm pursuing my computer science engineering in the data science specialization. So, sir,
Okay.
I wanted to ask one question, right? Are we having any programming assignments in the course? Like, we have to implement some
Mm,
uh,
not exactly.
algorithm.
Yeah, there would be, I guess there is. Uh, you might be asked to write some R code or actually check the R code that whether it's correct or not, because most of the course will be using R. But in examination, no examination you would not have. In this thing, I think there is, but sort of not
Yes, sir.
exactly submitting an this your, I mean, code, but rather than just checking whether the code is correct or not.
Okay. Sir,
Or
and
what?
one more thing.
Yeah, yeah.
Yeah, this time series analysis is like very essential in stock market prediction and all. So, if we do
Right.
this course, sir, if we do this course, can we expect some like uh, we can
Profit
do
returns.
any other
Acha.
quantity finance, quantity finance and related fields?
Yeah,
If
this
I
is
want to
related to
do,
that quantitative finance. That's correct, but I'm not sure that you will make money after because that is dependent upon. See, Once Newton himself has said that he himself can predict the motion of heavenly bodies, but he cannot predict the madness of humans. So similarly, is the stock market. Stock market is the madness of humans, and I'm pretty sure that, I mean, see, you will gain insights. You will be able to predict a lot of things, and there are pretty good chances that if you are an experienced stock share market and all these things, finance person, you will be able to escalate your profits. But just by learning this course, no, sorry, you cannot have good profit returns, because if that would have been the case, this would have been the most taken course. I mean, everyone would have been just doing this only.
Sir, one more thing. I before like before the course commenced on 28th January, I took a course on data camp. Like exactly the same thing they were teaching. Like time series analysis, it was with R only. So they
Mm-hmm.
taught with like started with functions like autoplot and all, and they went on to build on those concepts. So do you think that would be beneficial if I have already
That
done
is
a
more
course
of application,
on?
because I understood that that course I've heard of, and but that course is mostly on applications. See, this course that we are doing will give you a more general and more theoretical based idea. It do has applications, and there would be application based uh, problems also, but uh, if, I mean, that course that you're talking about, if you do this and that's simultaneously, and you're able to see, either you can do that course later and first do this course, or do it simultaneously, because what you learn in this theory, you will you will be able to have greater impact on using that in application, and might be possible that you come up with your own models or own predictions, because there you would have something well defined already being used, or that are mostly available, but here you will be able to build those things. More theoretical knowledge is here. And without theoretical knowledge, applications are extremely difficult to make. So I just suggest.
Okay,
Hmm.
thank you, sir.
Okay, Rohit. So in case of chemical engineers, no. So are you BTech chemical engineer, or you're doing masters or PhD, or you are in industry? Acha, BTech. You are doing BTech. So see, what happens is, in industry we see a lot of modeling that will come in your future. I mean, if you come into your fourth year, no, you will see a lot of modeling has started. Process modeling will begin, and on the surface only, a lot of people just see the model and then they go. But like Aspen, true. People, I have taught Aspen also. So when we teach Aspen, when we use Aspen to model a lot of data are from industry, we have this inherent problem that we do not see the uncertainties that are there, and then these uncertainties multiply, and we are not able to grasp those. I mean, not, we are unable to have the parameter estimation in a real process, and that is the worst part, that even as a chemical engineer, that all other engineers rely to make up those processes and design those processes, we are unable to actually bring that thing to real time working. Even though, let's say, just for example, we learn heat exchanger, all this reaction engineering we do, water flowing through a pipe, we see that how velocities change in those pipe. All of that have several assumptions, and those assumptions are deterministic. But once you bring into real life, there will be a lot of uncertainties and issues that you will not be able to solve. I mean, you will be stuck, and some or the other way because of those roughness and all those things. Even, for example, those models that Prandtl, Kolmogorov, turbulence models have come after understanding time series analysis. So this is extremely important course, but is a little advanced. I mean, see, what we learn in BTech is very deterministic. We just learn. Okay, let's say I have a line that has an equation y equals to mx plus c. X changes independently. Y is a dependent variable. Everything is very good, straightforward. That thing, but here you will have all sort of errors, and still you have to fix that line into the place. That's the question that we are trying to answer, and there are a lot of things. So you will see a lot of things that will come up. So let's start with the course. Just one second. Someone asked something. Okay, welcome. See, time series analysis. We have this term, time series analysis. This word time is actually, when it started, it had this component of time. I mean, with time we want to see how things move forward. But time series analysis would not only focus on our independent variable being time, but anything. You can have, let's say, how in stock market your things are changing, your prices are changing. This, all of this could happen in time. That is one thing. But you can also see that if in, for example, let's say you have, I'm taking a very random this thing examples. So a number of uh, donuts one shop sells, and how does the number of pastries that are being sold, these are two different things, but is there a correlation? That is also sort of a time series question. Actually, it comes in regression also, but regression itself is a part of time series analysis. You, in medicals, we see that we have this heartbeat sort of thing. All of this is periodic in nature, and based upon these things also medical experts are able to detect or say something or the other about the health of the patient. Apart from this, uh, in, let's say, in X you have temperature changing, or let's say it is changing in a more radical I mean, random fashion. All of this, it could be temperature, it could be velocities, all of this, if we are trying to make a sense of things, if we are trying to make some understanding from it, then it comes on time series analysis, irrespective of what is the independent variable. Oh, sorry, one second. New slide. See, time series analysis, let's say I have, uh, I do an experiment, let's say, in a lab. That could be all, I mean, it's not, I'm just taking an example. It could be the raw data that you have taken from a price of a stock, or it could be your, let's say, several signals have been received by the antenna. So those things, one second, sorry. So these all data is there. Now when this data is captured, that is data acquisition. This data itself is extremely raw. I mean, what you collect, what you measure through sensors, through your eyes, whatever it could be, is itself raw. It has to go several steps of, where is that, pre-processing and clearing, visualizations, understanding what model to be used, or what sort of, rather than what model has to be used, what type of model has to be used. Then we come up with actually starting analysis, that time series analysis. So all of this itself is extremely important, because like the 80-20 rule you have, which says that in order to achieve that 80%, I mean, you, the 20% of your results or 20% of your work, hard work, depends upon the 80% of the time you in, put in, and rest becomes clearer as that 20% becomes complete. Similarly, it is like in HR management, you will see that the 20% of the people in the company would actually be making 80% of the revenue of the company. So this 20-80 rules apply a lot of places, but for us it would be like most of the thing that we do, this 80% of the work is here, and then comes this analysis. This is 20%, but in order to reach this 20%, you have to do all of these things. For example, let's say I take a image of a, let's say, a smiling face. This smiling face would automatically be actually divided into several pixels. If I had to make, let's say, a AI model or some ML models in order to detect that face, I had to first acquire this data, pre-process it, put some analysis that with respect to time this will change, or with respect to position these intensities change, or what is the shape, this edge detection, all of this has to come first through this pre-processing, that we find out the characteristics of this data and then start to analyze it. Achha, can any one of you tell me that in real time, because okay, even I guess Pavan would be able to tell us that how to make a square wave. Pavan?
Yeah, like you have a DC source and you can take a switch which like turns on and off.
True. So when it is you have this DC source and you let's say a switch is there and turn on and off, you, I'm making this square wave. But let's say I talk you about mathematically. I have a AC source, okay, which has this. Sorry, not this one. I have an AC source. Automatically, you will see that there is a sine wave,
Hmm.
right?
Hmm.
Is this possible somehow that using sine waves or something you can come up with making a square wave?
Hmm. Uh, clipper circuits
Hmm. So
kind of
what
thing.
those clipper circuits do?
Uh, but we'll be getting a kind of like a ripple uh, using.
Okay,
Uh,
one second, one second. That's okay. You're good. What I'm saying is, let's say you have a sine wave.
yeah.
We can have with multiple sine waves. What happens
Ah,
is, if you have sine x plus sine 3x
okay.
plus a lot of these sine waves, when you start to add them up, no, slowly
Huh.
and gradually you will realize you are starting to make these square waves.
Yeah. Basically, it's kind of like Fourier series.
Yeah, and what
Huh.
Fourier series tells us, so if in real time we want to do this, we have to find out what are sine waves. And all of this comes under spectral analysis, which is a part of time series analysis. So let's say if I have some image of a smiling face or a data that is transmitted. If I want to extract something important from this, I have to go through some or the other analysis first to make something important for predictions. Here, using this, I will be able to detect many more smileys right now for this, from which if I say it's not smileys but faces, which is right now used in a lot of airports. You will see that there is some app known as DigiYatra, and a lot of places if you just go put your pass, no, boarding pass, upload that in it, you don't have to stand in lines at airport. The When you go there, the camera will scan your face. It will recognize some features that you have already put in your data from the DigiYatra app, and it will automatically allow you, though human intervention itself is not allowed. I mean, it's not allowed, but it's not required. And let's say if I have some data that is being uh, coming, I can first reduce them into several peaks from Fourier analysis, remove the noises that I feel that they are inherently there, and then recombine it. That is also part of time series analysis. So time series analysis is actually very wide, but our main focus is to actually see that whether there is uh, any predictions that we can do, because in a lot of data that is coming, you have a lot of this database. From this you can say all of these are noises. I just to remove them. Similarly, their spectral analysis, their periodicity, is there any periodic nature of the data or anything. So predicting spectral means finding out specific features, periodic nature, and classifying based upon the features that we have encountered. Does anyone has a doubt on all these four type of things that time series analysis can do?
Actually, I think this spectral analysis and this periodicities are one on the same thing, because the Fourier means from the Fourier spectrum we would have the list of frequencies that are present, and from that we can determine the fundamental frequency and the time period. So aren't they the one and same?
No, I tell you why. Uh, let's say seasons. Every season, when changes, the cost of your AC I mean cost of electricity bill rises and goes down, right? And you have uh, but that is dependent upon whether, I mean, what is the seasonal range, or let's say this time, I mean, in northern India, you will find that there is a less of cold, or something has been delayed. That is a period. There are some errors in this periodic, but in spectral analysis, you actually separate all those. Here what you're doing is, uh let's say, I mean, first, one example, 1 minute. In January, let's say you have low cost. February, you have still low cost, but in March you have higher cost. In July, you have very high cost. Sorry, not here. August, you still have high cost, but then it starts to plummet and goes to something. This goes year in year. Okay. And if I go to 5 year data, it would be sort of like, but there will be so many. If you zoom in, no, you will find a lot of small trenches and all. But I mean, not but in the contrast, you have several frequencies in signal. Or let's say, if I tell you that there are some deterministic errors, or let's say noises in your data, and you want to find out what are those, then you can actually peek them out. That, okay, let's say this is the peak that is an error. I just have want to remove this, and then you will be able to. So you have in this frequency domain, these peaks are there, and they form your signal. There's also sort of a deterministic errors. But in case of when your prices of your AC is going up and down, I mean, for the light expenses going up and down, they are spread across a lot of variables. They cannot be distinguished between spectra. So we have another kind of analysis in order to see the periodicity of those errors. So yeah, your point of saying that periodicity and spectral analysis are two different, are seem to be different, but are same, one and the same. But both of them work in different domain of problems. One, signal processing or spectral analysis, more of work in a deterministic errors, where you have frequency domain, and it little bit errors are defined in those frequency domains. But uh, rather than in periodicity, in these periodic analysis, you still have time series, but these errors are not deterministic. That is the difference.
Okay, that means it is power spectral density that you're talking about, wherein we deal with the random signals, and therein after we study this PhDs.
Hmm. So there would be errors. I'm not saying that there would be no randomness in spectral analysis. There would be, but it would be still deterministic. But apart from this, in periodic analysis, you will see periodic, but that are not possible to convert into frequency domain, or they are much more random that they cannot be classified into errors itself.
Yeah, got it. Yeah, got it.
Okay. See, what happens is when we are doing this time series analysis, once one part is science, one part is art. In this course, you will actually find out that you understand all these formula, protocols, algorithms, methods, all these things you will encounter. The notion or the approach behind these concepts will also be taught, but how to apply them is more of a practical sense. Like all those mathematicians, we all of us know that how to differentiate, how to integrate, but many of the questions that so does anyone know about the seven millennial problems?
No.
Okay, so see, there as there's a mathematical institute, Clay Mathematical Institute, which has posed uh, seven problems, out of which two have been solved, and each problem worth $1 million. So if you are able to solve that problem, you will get $1 million. Two problems have been solved, and all of those problems are basic to mathematics and science itself. They make, and one of those problems is actually Navier-Stokes equation. That how to have further understanding of that equation. What all these equations have? Basic. I mean, they are also trying to replicate what is there in the real time. But the art of these equations come when these equations become famous, when you have a certain way of doing that, the protocols and how to make that. Your data itself is so clumsy, your data itself is so crowded, that how to clear that data, which method has to be done first, and why, which parameter has to be set in certain way, all of this, finding out that estimation makes that art. Knowing all what can we do is science, but doing that in a subtle way such that we have the most best out of your data is that art. And data science people only get paid for this thing only, that they are the artists who are able to make best out of their data. Okay, so we have talked about that we are able in time series analysis we will see this science part, we will see all those formulas, but what we will also see is that there are two types of problems that we will encounter. One thing, if you have some observation, whatever observation you want to have, you can have it. It would have some deterministic part plus some stochastic part. Deterministic part is from first principles. As a matter of fact, we will, I mean, the assumption that time series analysis takes is that everything is non-deterministic, everything is stochastic. Then we later on realize that there is some part that is deterministic, and then we work on it. So there would be a problem where it is deterministic part is also there and stochastic part is also there, just like turbulent equation, turbulence and entropy or whatever things are there. Or there would be no deterministic part, only stochastic part, like stock market is a lot of stochastic, but still we have to make predictions. In this both of the problem, we will not be having those equations or those problems where there is no stochastic or deterministic, because that is already we have been learning. Y equals to mx plus c or y equals to x square is a equation of certain lines and parabolas, that is deterministic. But from data that is unclear, you make those predictions. That is the observation, or that is the science analysis. Now moving on, uh, let's talk about randomness, because all those errors that we encounter in time series analysis will have a sort of randomness. Can anyone tell me what randomness it's is about? I mean, what does it mean? Something to be random.
Uh, Basically, we cannot be sure about the outcome even if we perform the same like experiment in a similar condition. So the outcomes will be different each time.
Hmm. I would not say they will be different each time, but what I would say, you
Yeah,
cannot accurately predict.
predict accurately predict. Yeah.
So basically, I think it's a lag. Means we cannot formulate a mathematical equation describing the input-output relation from minus t equal to infinity to positive infinity.
Hmm. You all are right. That's correct. Randomness is about not being able to predict or tell based upon the infinite amount of data that is given. And a true random, a ideal random data would be where the best solution or best possible prediction is average. Average of all data. If that is the best you can come up with, is a truly ideal random process of phenomena. And if you are able to predict some part, that is sort of non-ideality that has come into randomness. Just for example, let's say I have a bacteria. So I'm a chemical engineer who actually I'm a PhD in chemical engineering. I'm doing my PhD in chemical engineering. I'm actually right now studying that how bacteria moves. And I must tell you, it's a hell in understanding how bacteria moves. Because when bacteria is moving, it can come encounter another bacteria. It can encounter some chemical. It can encounter anything. And it will change its direction based upon God knows what. I mean, there's a lot of things that are simultaneously happening, and we cannot tell why it is happening. But irrespective of that, we are still able to find out some or the other thing. For example, it's if I plot, sorry, if I plot MSD versus time, I see a straight line in log scale. And this slope will actually we what we do is MSD equals to 4 d t to the power alpha, and this tells us whether our bacteria is living or is it dead based upon this alpha. So if, because see, there are several molecules. If you go down into the microscope at very small scales, there the pollen grains, the small dust particles, they will also move randomly. They will also have this thing. I mean the straight line. But how is the slope changing? Is this alpha? This will actually tell me that whether it's live or dead. Or see, if my alpha is between 1 to 2, specifically near 2, then I will say yeah, it is living, it is moving on its own, it has active motion. But if it is alpha is equals to 1, then I will say no. Alpha, sorry, where? Alpha equals to 1. I will say no, it is a Brownian motion. There's nothing. And if alpha is less than 1, then I'm pretty sure that it is dead. It is now being slowed down. It is being attracted to something or the other. It's getting attached. All of that comes from understanding that how bacterial motion is there, which you cannot find out whether it's dead or live just by seeing it, but its motion tracking, understanding how that happens, is able to tell me a lot of things. So this is just an real time example that how uh, time series analysis is will be able to help you predict a lot of things. And randomness, because even though bacteria is moving randomly in any direction, still I'm able to see that whether is it moving in such a way predicted that I want or not. Anyone has a question on this?
Yeah, I thought that it was a Brownian motion. So I didn't knew about that. If it is there, then it is not a Brownian motion.
Okay. See, Brownian motion says that this alpha is equals to 1. That you are sure, right?
Yeah.
Okay. What happen is when bacteria has this flagella, no, it goes, I mean, when it is moving in a certain direction, it will move such that your alpha equals to 2. The motion is active, it's trying from its own flagella also and being hit by other molecules also. So there's Brownian motion plus the active energy that the bacteria has applied in order to push forward. But what happens is slowly and gradually that it changes direction and becomes near to or less than 2. This motion is actually ballistic. It has been learned in literature that this motion of when alpha is equals to 2 is known as ballistic motion. When alpha equals to 1 is known as Brownian motion. Alpha equals to 2 is known as ballistic motion. And uh, the energy that is being used increases that MSD in a square fashion with this time. This has been learned and observed with this over several years in literature. But if you ask me, how do you know that this is two and this is has to be that way? Sorry, this does not come from first principle. It comes from a model that has been made from the data. Brownian motion, the alpha equals to 1 has come from the first principle that Einstein had the derivation. But when we started to applying on many more cases, then we understood that there is a more generalized form for which alpha has been put as a generalization. That is when you see apply this randomness or the time series analysis. Have I answered your question?
Yeah, I got it.
See, source of this randomness. Or error. See, randomness, if I say randomness also, this is actually sort of error also for me. Because if I start to model my motion of bacteria that is moving like this, all these changes that happens, the small wiggles that happen are errors for me. But that is the same thing as randomness. On which direction will it choose? This is random. And there's an error part to it. That is why I'm using randomness and error only for this part, as I mean sort of mix, not exactly different. So sources of these errors or randomness mostly come from unawareness to processes. When people are not aware of the processes that happen. See, I am right now, for me this bacteria moving like this is I mean, hey, it's randomly moving. But when I go deep and deep, I find that there is source of food here, or let's say a chemical that is there, that is bacteria getting attracted. So then only I will see, oh no, it's not random, this is based upon some gradient. It is based upon some process of sensing and then moving. So unaware of the processes is one of the source of randomness and uncertainties that we encounter. Other thing is measurement. In this bacterial analysis, bacteria only, when it is moving, I can, I'm capturing using a microscope. So I'm taking a video. That video would have some frame rate in FPS. Let's say it has some 10 FPS. There are, I can take in 20 FPS also. I can take in 30 FPS also. These are three different measure cases of measurement. But what happens is, in each measurement that I'm taking, I am losing or gaining some of the other data. In 10 FPS, I would be seeing that, okay, first position here, second position here. One second. I'll just change. Yeah, first position here, second position here, third position here, fourth here, fifth here, sixth here, just like that. In 20 FPS, I will be able to see that, okay, this position is also there, this is also there, this is also there. In 30 FPS, I saw that when bacteria is coming here, it is actually first stopping, then rotating, and then started to move. That in 30 FPS, which I was not able to see in 10 FPS. So that is how we take the measurement. How we acquire data. You all the signals that we take from electrical, if you have so you might have seen that antennas are sort of like this design. You know why this design is there? In old TV sort of also they had this sort of design of antenna. Can anyone tell me why this design?
I think the number of sticks can increase your signal reception probability.
Good, but not true. That's true. That happens. Your signal carrying capacity increases, but this sizes no. If
Yeah,
I
the size. Yeah, the size is also means the dipole should have a particular size to receive a particular frequency signal.
So what happened is, so this is actually a very famous story. When people were designing these antennas, they wanted different sizes, because these antenna will, when the signal will come to them, based upon the size of this or the difference in the different antennas, it will capture that frequency. Now what happen is, if you cannot have all the several sizes, if your frequency range lies from, let's say, 1000 hertz to 2000 hertz, you cannot have at every 1 hertz. So the size of that antenna cannot be in every of every sizes. So what the people did is, if you zoom in this, no, you'll find out that this also had several of these, and then they had several of these. They started making a sort of fractal dimension, and uh, had an infinite perimeter, but finite volume. This was a concept, and then they stopped at a certain resolution. Key, okay, fine, it's okay if I will change based upon every 10 hertz I will have that frequency. This was the concept of making into this design. So how to measure, the way of measuring the design is very, the signal or the data is very important. and there are some things that are not controlled. So I could actually, if in case of bacteria, if I take 40 fps, I might be able to see some better motion or something or the other that I have not ever seen. Even let's say if you go in antenna design, you might be able to see better and better resolution of signals. You might be able to clear the data, but that comes as a cost. The taking 40 fps is not possible with my instrument, or making that instrument itself for antenna is also not possible. So there are some things, some parameters, some measurement processes that are not in our control. So that causes the uncertainties. Then comes the last one, and actually funny one, unknown. You do not know. You do not itself know what's the reason of having those uncertainties, or they're not measurable. Let's say I take you, if I am having a heat exchanger or just a tube, you have those AC, no? So ACs have these copper tubes. These copper tubes would have roughness on their surface. Your hot fluid is going inside, and you have cold fluid inside. The heat will be transmitted from the hot to the cold, and you will get that cold uh, outside. I mean that is when evaporator is there. That's the outside sink, and opposite will happen inside. That the cool air will spread inside the room, and the hot heat will be taken by the fluid from the AC. There are several factors that come into place, but in models we try to make assumptions. But some uncertainties because of the roughness of the copper tube will occur that we have never encountered in our models. Because of these unmeasurable or unknown factors, unknown certainties or source of error come into place. And because of this reason only, we have to move from deterministic model, or let's say mathematics to probabilistic maths. Sorry, I have a parrot that is at my behind, and he's constantly speaking. I'm sorry for that. Yeah, so we have to move into a probabilistic mathematics, because randomness is not about may or may not be, or uncertainty key. Let's say if I have a cloud that is there, someone said something. Acha, okay, right. So what is the uh yeah, so Abhinav, yeah, this is there in the course. Then how to build a model and what works, what does not work, that is there in the course. And from scratch, you can do that. And for Rohit, the data regarding that bacterial motion is important in water disinfection. So what happened is we try to make strategies such that that bacteria gets trapped and gets killed. That is and what strategy. So for example, if I have a filter using activated carbon, how will I have that bacteria moving in that, and in such a way that my bacteria is, I mean, let me tell you. See, let's say if I have some bends like these, okay, bacteria is coming, there is water is flowing inside there, bacteria is coming, and at what speed that bacteria will hit this wall, such that whatever killing agent that I have put on this wall kills the bacteria, or at will it be able to change its direction such that it evades that killing agent. This is the question that is the at the heart of the understanding the bacterial motion. I mean, the reason that I study the bacterial motion. And if the bacteria is not able to uh, I mean change the direction, or it's getting killed, that's the best thing that I want to happen to the bacteria. Not fortunate for the bacteria, at least. Okay. So something. Okay. See, what happened is we have to move into a probabilistic framework, and sir has actually given his a lot of data that see what probability is something. I mean, see, some of your of the class is actually already in mathematics and statistics. They would already know a lot of probability, and that is actually a prerequisite of this course also. But if students want, if everyone wants me to teach that probability also, I'm happy to do that. I have no issues, because sir takes actually about 4 or 5 sessions. Then only he goes on with this probability. That's what he has told. Else we can skip the
Uh,
topic.
Actually, I had a doubt regarding one of the concepts.
Tell
Uh,
me.
Basically, it's about this one. Can you explain confounding and this partial correlation? Uh, uh, the concept of confounding and partial correlation, and can you give a practical example where, like a real life example where it's actually comes into use?
Confounding and
Partial correlation. Say
sorry, I didn't.
partial correlation.
A partial correlation. Okay, okay. I was thinking of bachelor correlation. I'm sorry.
No.
Okay, partial correlation. Hmm. Um. Do you know COE, coefficient of variance?
What I didn't get.
Did you know coefficient of a COV? When, let's say, if I have x, y, these are two independent variables that affect my function f.
Uh,
F is a function of x and y.
okay.
And x and y are two, let's say, for example, pressure and temperature. Oh, not pressure and temperature. Let's say if there's a gas that is filled inside the room, okay,
Yeah.
and the volume of the gas
Yeah.
is dependent upon the pressure and temperature.
Huh.
Okay,
Hmm.
basic 12th class thing.
Hmm.
Ideal gas equation. Okay, now x and y, these are two things that are itself working on f
Hmm.
independently, but there would be something or the other that if x affects y or y affects x, there would be some correlation that is being formed.
Hmm.
That is that partial correlation, that how uh, x affects y, sorry, x affects f irrespective of y affects f irrespective of x, and how they both interact with each other. That is what partial correlation tells us.
But X and Y are independent of each other.
Yes, they should be independent of each other, but
Okay.
in reality they are not. It That is
Ah.
the problem, that when we say, I assumed that pressure and temperature are independent of each other. I measure both of them, but I soon found out that they are not, they have some or the other small relation. And okay, let is a very simple example that is very interesting also. the size of the shoe and the uh, size, no, the number of the income of your person. Two things: size of the shoe and income of the person. These two are independent or dependent on each other.
Income and size, like they are independent.
They are independent,
Yeah.
but there is a correlation.
Okay.
What do you think is the reason for this?
Correlation like tells us there is a dependency.
There's a
And
dependence. That's correct. I mean, I can see that as size, there's a trend there. The size and the income, as size increase, income is increasing. So, real scenario is that I am a person. I am a human being. As when I was a small kid, my size of the shoe was very small. As my age grew, my size increased, and I started earning. So my income increased. This
okay.
is some, both of them are related to me,
Huh.
but these two variables are independent.
Okay. Yeah, nice.
So
But
that's
but it also depends on the modeling. Let's say that if I'm freezing the time, let's say the age is constant, and if I then try to draw this assumption, and it wouldn't hold, right?
right, true. But in real time processes or real time phenomena, we actually never know what's the full scenario. That is where the source of uncertainty comes. That was
Hmm.
the first thing, that we do not know the full process. I just
Hmm.
asked him the size and income. That's it. Both are increasing. So, what his instinct would be? His instinct would form a correlation. But what happens a lot of time is we are unable to form a correlation. I mean, that correlation is absurd.
Hmm.
It has no meaning. There is no point of having size and income being interrelated. But that comes into play, and there is some of the other back processes happening. So, partial correlation actually tells us that there's something at the back that is happening, and you have to figure that out. I'm not exactly for confounding. I will later explain, because I'm not right now in a this thing. Not thinking of any example that will help me tell you confounding. But I will just surely tell you in
Okay.
next class. Uh, what's the time? Just 1 second. Um, just 1 second. Has anyone? Does anyone know about that? What, garbage in, garbage out?
No.
So this is just a very good phrase that people use in modeling, because correlation does not mean causation, MEAN, causation, and whatever data, irrespective of how good model you have. Sorry, just 1 second. Let's say if I have a model. Oh, this pad is not writing well. Input, output. One thing can happen is your input is bad. There's a lot of outliers. There are a lot of these things, uh, errors. Then just 1 second. irrespective of how good your model it could be, your output itself would be bad. And if you have very good input, your and your model is bad, then your output will be bad. There are two cases that will happen. And in time series analysis, when we have the data acquisition, we take out first missing values and outliers. These are two main things that we have to focus on to remove or add them. For example, from a basic principle, I would know that at time t equal to 0, my position of all the bacteria was 0. But that has not been captured by the this thing, by the model. I mean, by the data that I've taken. It starts from t equal to 1, let's say. So I know that t equal to 0 it was there, and that's a basic principle. So I have to add that data. I cannot assume the data that my equations or model would take that. Or let's say these are some like boundary conditions. So when we have this velocity that is flowing in pipe, we put this assumption. We put this assumption that the velocity is 0 at the walls. That is a data that we have to put. So that are the missing values. So in sciences, when we are studying, or even let's say you had the stock analysis, in stocks there are some rise or downs. History is there. There could be some places where the history is unknown. History is not known. For those cases, just give me a minute. Okay, so sorry. So for those history is not known. In those cases, these are the missing values that you have to put. And apart from that, let's say, okay, I think you all might maybe knowing it. Let's say if I have some data, you are seeing that it is increasing with time, but there's some data here, some data here. That could have been possible because of uh, what? Maybe measure uh, I mean measurable techniques that are there that are in kind of, or some external in errors might have come. That could be one reason. So we have to find out, and what we do is we take these values, we divide the range. So this is, if this is the range, total range, we divide it into quartiles, 1/4, and so 0 to 1/4 quartile, and 3/4 to 1. These are those that we can actually remove. And from 1/4 to 3/4, that is the half of the data that we can take if we are having a notion that there are a lot of outliers. And that actually happens, that actually helps, because a lot of data is actually in the middle only of the range. Range, when I'm talking the value of y's, not x. We can have in opposite also. We can take from x also. This type of the data processing actually helps a lot. And once you're done with that, you find out that whether your estimate, the change that you made, was in the range of the variation of, let's say, I had this data points when I was having these outliers. I was fitting the data. I was having some r square value, let's say 0.8. Then when I remove those outliers, I had r square value as 0.9. There was some slope mean value was also there. Was it even, I mean, when I did that, when I removed these two data, did slope value change significantly? All these questions become the heart of this thing, because the p value, so you can do that hypothesis testing in that, and you can see whether the p value is below 0.05 or not. If they yes, then hypothesis testing is true, false, null hypothesis comes true, all of that situations come, and that forms the first basis of your data processing. That's the first part. Then comes the second part. You start to see. One second, I'll add more. Do you have the question in this? Whether, I mean, checking, adding missing values or removing outliers? There are several more methods that will come into play. There are many more techniques that people can apply, but I'm telling in a very crude form. I sorry, Rohit, that I cannot show right now. I will show you uh, later on sometime. Yeah. So what was the case? So what happens? Let's say Winter Olympics is happening. Okay. Olympics is happening, and you want to see that on Earth, if let's say you are there, when you go in upper regions, let's say in America, then you go to Ireland, the number of gold medals, does it increase or decrease? That's a very very random process. I mean, that is, you cannot directly correlate or relate. One could obviously think that if people are living in the colder regions are much more active and better in winter, so yeah, it should increase or it should decrease, or that could come as a surprise that maybe those colder regions are much more wealthy, or there are some several factors that will come into play. But that's a question that you have, that's a real life question, because based upon this only a lot of people start betting, or they start their bids. Even companies also have sort of this in stock markets also. So how to do that? From the history, people start uh, have this data that as latitude increase, the number of gold medals. How to build that from the data, how to build a model. So what people do is they first have this y equals to mx plus beta. Let's say this is your first line. M x is your first variable that you're thinking of. So from this you start to regress. Okay. Let's say I fit this straight line here. I'm right now talking about linear regression only. There could be other regression based upon your art. So that is where art comes. I could have done actually x square also. I could have taken that x square is there. But right now I'm taking only linear form. Cut. So right now I'm taking linear only. So what will happen? I will have this y equals to mx. Then I will get this m value. I will subtract this uh, y hat. Let's say mx value from these value. Then I will get something of a more random this data. This more random I have to make sense, and I will start looking for more variables. Once I look for more variables, I will encounter there are okay. One was population, one was poverty, one was GDP or something like that. So slowly and gradually, these errors, these oscillations will go off, and what I will see is a good model that is there. And this way of doing is comes under regression, that how linear we regress. This is one way. Apart from this, people also come up with autocorrelation functions, which they start to see that, let's say, uh, I have these 3 points, I'll first correlate with them. Then what is the r square value? Then I will move to fourth point. What is the r square value? Fifth point, r square value. Sixth point, r square value. The time when this r square value starts to drop is the point where your correlation has stopped. And you can actually say that, okay, till this time correlation was there and I can have. So for a extremely random process, this will come down soon. Your r square value for first few things would be 1, and then it will come down. For a completely deterministic process, this will always remain 1. Let's say a line. If a points are in a line, obviously r square value will always remain 1. For some process like let's say bacteria thing, it slowly came down here. It was not exactly random, it was not exactly deterministic, it was somewhere in the between. That becomes your sort of model that helps in model making. And what people do is then they cut off till when they have put a threshold. Let's say I say that till 90% of my r square. Okay, let's say 0.9. If that is my threshold, I will have this point as my threshold, and before that, I will take plot my regression, and I have will have those motility or diffusivity values, for example. Or let's say in economics, if you go, for example, you have population and n- number of millionaires. For this also you will have something, some data. This could be like that, that initially when there's very less population, there is not much, but then there is increase, and then there's decrease in number of millionaires. For example, if you see countries like what very small countries, Maldives, let's say, they have population is very less, millionaires are also very less. If you go to United Kingdom, you will see they have a less population but more than Maldives, and the number of millionaires are much more. If you go to come to India, you will see population is extremely huge, but number of millionaires with respect to that is very less. So there is a trade-off that comes in between, and that we have to start to model. So in order to do that, what we will do, we will first find out this thing, a line, a equation, or whatever that we fits the best, and then we start to slowly see the errors. And apart from that, we will also see that how these regress to themselves. I will start forming small clusters and see my whether my model is able to have this r square coming to random or straight or whatever it could be. That's still a very unknown process. And it is not that it only goes down. There are cases when actually it goes down up, and that is the most funniest part, because what happen is, for example, when my bacteria is moving, it comes and turn around. When it turns around, the regression actually comes up. There's a dip in between and there's a up. That all of this is sort of a way of checking or finding models and validating models and using them to see that what parameters estimation is there. Okay, so 30 minutes are left. I guess we can take some questions if we have, or whatever you think. Because see, first week is more of a review, overview, and building interest. If you have any questions that you want to ask, or anything you want to discuss in next class, you can obviously ask me here. Being a chemical engineer, how do you come across time series analysis? Okay, so obviously told you about bacteria, but as a chemical engineer I came across because in uh, for example, Reliance Industries, my friends work in Reliance Industries, and I've seen in Gale also. Even in there is Aarti Industries, they have several processes, and the temperature fluctuations in these processes. For example, Aarti Industries had this question. So I tell you their problem. This is a real and true story. I mean, not a story, a true problem that they encounter. I wish they do not put any bad name on me. But let's say what they have two molecules A and B. Both are isomers of each other. They have to just separate them. But while separating, distillation is not a possibility, because they are isomers and their boiling point is 1 or 2 degrees apart. So their distillation is extremely inefficient. So what they go through a crystallization process. So what they do is they first decrease the temperature below 0 degrees Celsius, about minus 40 degrees Celsius. Then there is crystallization that happens on the walls of the tubes, and they start to increase, and they increase it up to 60 degrees Celsius, and then they increase in here. This is the same process that they do. Now in this, the sensor that captures it, no, is, I mean, it does not always at the same time it will capture the same data. That's not the case. The sensors are itself very error based. They have errors. So we have to regress it in such a fashion that we find out when is the nucleation actually happening. We found out that the nucleation starts at this point or this point. Then is there a possibility that we reduce this time, because this process hold takes about 60 hours, but lab experiments tell that this is possible in 40 hours itself. So what is the process, or what thing can we do in this process that we reduce this time from 60 hours to 40 hours? That was a question that was put to us. In order to do that, we did a lot of simulations, we did a lot of time series analysis to find out that, okay, if I just the rate of my cooling, if I increase it and go to this place instead rather than within time, I could actually have a steep increase, and this will actually save time. So all of this will shorten my go temperature will go like somewhat like this, and then there's a slope. This temperature, and that is possible if I change the flow rate of the cooling water. This small change of cooling water was proposed to the this thing Aarti industry. They implemented it. I do not know what the results came up, but this was a very good exercise which actually helped in having the minimal solution, because the true solution would have been, I mean, if a person has a lot of money, what they can do, they can start rebuilding years of experimentation and all. But just without going all of that tedious process and expensive one also, we just came up with a very small solution to change the valve and increase the flow rate. That's it. And which helped. Actually, with simulation, I do not know what the two results, because they will actually not tell me this thing, what happened to the solution, but that's okay. Okay, anything else? 1 second. I had one SEM course on problem solving, but it didn't cover hypothesis testing, autocorrelation. These things should be learned from this course. Yes, 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 yes. You will learn all of this in this course. Hypothesis testing, no. Sir would actually in next week, I mean in this week also he might have done. So he would cover sort of hypothesis testing and all, but I would actually go through in next class. I will go through all of the probability, how to test hypothesis, whether it's a null hypothesis, it's a false positive, or all these things I will cover. If sir has not covered it, I will cover it. Did we solve the problem with the help of time series analysis? Yes, we solved the problem through time series analysis. We actually solve a lot of issues using time series analysis, because and sometimes it happens, no, we ourselves are not able to uh, see that time series analysis is a very wise, I mean, uh, wide range of data. Climate itself is predicted because of time series analysis. We are able to predict a lot of things. So time series analysis is about predicting that this will happen, this random variable will go in that way. All of this is done by time series analysis, but sometimes we do it, we do not know it that we are doing it. And our process or methods are also very weak, sort of. I would be very frank, it would be very weak, that we do not apply the good methods. We do not apply robust methods, and sometimes we end up having bad this thing. Uh, Solution is there, but it's not good, sort of, is not robust, that there are chances are very sensitive to sort of small changes. That's an issue. Fair enough, sir. Okay. mm, so I guess if I'm staying till 8, so if anyone has questions, we can actually next time it would be much more I mean, we will start through probability and statistics. We will cover all hypotheses, everything, and in next class we will have a lot of things more. So for this session, it's this much only. I'm here till 8. If you have any questions, you can ask, even from the course also. Some coding exercises in R applying some stats concept. Ah, Okay, if you want, we can do that R also. So actually, I myself is proficient in MATLAB, not specifically in R, but because this course wants to use an R only. I mean, sir has proposed two course textbooks. One uses MATLAB, one uses R. So anyone we can use for our questions, but R is what sir is wants us to do. So that's okay. We will do R only. And if you want, I can teach R also, but that will be very small. I mean, we'll go one by one. How can we use time series as a stock forecasting scan, such as which hybrid ML model will be best for it? Hmm. I myself is not very. I mean, for ML, which model will be best for it? That I cannot tell. But yeah, how can we? For forecasting, you have to take at least 5 years of data. You have to apply what changes. So there's a lot of market research that happens now. Sees that when, for example, Adani's stock, if I talk about Adani's stock was whenever the new project in energy were coming, and Adani's energy some source was there. I mean, company was there. Whenever some these energy projects were coming, his stock rose a lot. So with respect to population, with respect to new projects that are coming, so I can say that one independent variable was the number of projects on the construction projects that were there. Based upon that, Adani's uh how Adani's this thing stock price increase, that is sort of a question that will help me in forming a model. This kind of forecasting can be done, and how much increase is there. So and whenever then this, so with increase in number of projects, prices increase. With a number of accusation or number of police complaints, prices decrease. Then with number of investors, prices increase or decrease. All of that is there. If I increase the number of investors, sometimes price decreases. Most of the cases, price increase. All of these questions are at the heart of stock forecasting, but I do not know whether, I mean, for ML modeling, how it could be done best, I am not sure about. But this course will not actually go into ML modeling, only forecasting would be there. Yes, if there is no data, then modeling cannot happen. But if you still want to predict it, there is one possibility. If, let's say, for example, I make a new molecule, okay, I'm taking a question from chemical engineering. So if someone is not able to understand, they can ask me. So if I want to make a new molecule, uh, I'm pretty sure I do not know its boiling point. I do not know its properties. But what people have done is people have based upon whatever functional compounds are there, what is the molecular weight, based upon that itself, what is the structure, people predict a lot of things, and from those predictions they can find out parameters, and then make do modeling. So if we do not have a data for some process or something that is actually we want to study, but there is something that is very near to that or very relatable, or at least I can break that data or information or experiment into parts that are known in literature or in real time for which data is available. Then you can do that. You have to just combine in a good fashion, and that combine is that combination good or bad is told by hypothesis testing, and then you can apply that modeling into time series analysis and then do it. So but time series analysis would require, I mean would actually tell for those related or very near models. It is possible. It's not impossible. It's possible, but it would have some errors on it of its own. In stock market, if you say, then also it is possible. Yeah, Kamal, you can ask or tell. Kamal, हाँ कमल. आई थिंक गलती से हो गया है, हाथ उड़ गया उसका. ओके फाइन. Okay, 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 you asked the question. Sir, actually, I want to build my own product in fintech domain. So, I get some roadmap for that. Fintech? What is fintech? Actually, I do not know what is fintech. And financial technology. Is it so? Okay, okay. Okay. So, your first roadmap would actually be data acquisition. That is a basic thing. If you want to build your own product in fintech, that will be your first step would be locate which are the original sources of data collection. Then there is a very good model. There's one model that actually predicts a lot of stock marketing in 1930s to 1960s. America and Europe had a lot of the stock markets. They were stock market still existed. So at that time, people actually started modeling, and that equation is the best equation that has come up till now. People have modified it a little bit or not less, but that is the best equation that is there in the market. I just forgot its name. Next time I have to write that equation of the stock prediction. That's a very famous equation. You can use that equation as your first trial. Once that is there, no, then from that basis you can start upon adding things. What do you think? Yes, that's a very good this thing. Black-Scholes equation. If I think that's right. Black-Scholes equation only. I've studied that. I'm actually not remembering. That has there in my mind, but I guess you're right. Black-Scholes only. Yeah. I'm not sure. I have to see that again. I saw that only for a very short period of time. I mean, 1 or 2 minutes. I was reading about that, but I'm not sure that if it's a question or not. But I guess Abhinav, you're right. And what do you think? So this is actually Kamal. This is actually a very good area for pursuing PhD. Uh, but the point is, PhD requires something to be novel. This equation, whichever I guess Black shows only, which Abhinav is talking about, that itself was a PhD thesis, and then only that if you do PhD thesis, or and this comes in physics actually, physics, economics, all of this you can do, and mathematics also. You can do PhD in that. And as a matter of fact, time series analysis will help you in that. Okay, so I will end the class now. If you have any other question, you can ask obviously. If none, I can end the class. Thank you. Okay, sorry, bye. In this session, discuss case studies. Yeah, sure. I will discuss case studies. Case Good night. Okay. Sorry. Bye bye. Thank you for coming.